The College of Arts and Sciences at Stony Brook University presents The Difference You Make, where we hear weekly from people who make a difference in our world. Here now, the Dean of the College of Arts and Sciences and Professor of History, our host, David Wrobel.
Hello, my name is David Wrobel, Dean and Professor of History in the College of Arts and Sciences at Stony Brook University. On today's episode of The Difference You Make, I'm joined by Barry Barish, world-renowned experimental physicist, Nobel Laureate, and Stony Brook University President's Distinguished Endowed Chair in Physics. Professor Barish has an extraordinary long list of achievements in the world of physics, including, of course, the Nobel Prize, and one other I want to mention. In 2023, Barry was awarded the prestigious National Medal of Science by President Joe Biden. This award is among the highest honors in the scientific community, and he was acknowledged for his exemplary service to science, including groundbreaking research on subatomic particles. So, Barry, welcome to the show.
Hi, David. Thank you.
Why don't we start right there with the incredible breakthrough that led to the Nobel Prize, the Laser Interferometer Gravitational-Wave Observatory, LIGO. As principal investigator and director of that operation, you orchestrated the construction and commissioning of LIGO's interferometers, leading to the historic detection of gravitational waves. This was in 2015, which validated Einstein's predictions and revolutionized astrophysics. Can we start there? Tell us a little bit about why it's so important that we understand that breakthrough and gravitational waves.
Yeah, well, we all know about electromagnetic waves. So gravitational waves, the idea, not so much the idea, the conjecture that there were gravitational waves began with Einstein. And we all live with electromagnetic waves every day, everything from radio waves to light itself, to X-rays, to everything in light. And Einstein noticed that if he looked at the equations of gravity that he had developed, called general relativity, in a particular way, they had a similarity to electromagnetic waves. That doesn't prove anything. But being Einstein, he made the leap that if that's true, maybe there were gravitational waves. He also said they could never be detected. And why? Because he couldn't anticipate the technologies that we've developed 100 years afterwards that have enabled us to detect them. But from those words, you can imagine they're extremely weak. So it's very hard to detect them.
And how does their sort of proof of their existence change our understanding of the physical world?
The whole physical world is governed by the forces and whatever the forces act on. And there's four forces in nature, period. That's it. Gravity, that holds us down to the earth. Electricity and magnetism are connected. What's called the weak interaction, which is the radioactive decay that we experience. And the strong interaction, which is what holds us together, nuclei together. So there's four forces in nature. And physics is basically understanding much of physics is understanding what those four forces are, how they interact with each other. There's a conjecture, words that get used, unification, grand unification that you hear, are that at somewhere in high enough energy, all those forces are the same. So we live in a world where they're different from each other, so gravity behaves different than electricity, and interactions which cause decay are a little different in our region of where we kind of experience life, but those forces are all connected. It's the job of physics and physicists to understand the laws of nature and how they originate and how they interact with each other. That's kind of one of our primary goals. So gravity is one of the biggest ones. And if gravity has waves like electromagnetism, it's kind of a big piece of putting that puzzle together.
The science or the process of doing the science on this sort of scale. There was a team of about 40 scientists, and it was scaled up to a massive team of about 1,000. How is that done, and what are the different sorts of contributions of people? How do you make all of that work together?
There were, as you said, there were about 40 people, scientists at two institutions at Caltech and MIT that pursued this idea and developed the techniques far enough to understand what to do and to demonstrate kind of the reality that you could, if you did it well enough, you could make a device that could detect gravitational waves. So that was when it was 30 or 40. But the device itself pushed everything to extreme limits. So let's, for example, say that the source of light that we use to make the instruments work are lasers, but the lasers that we use first are much more precise than, and that we need much more precise than lasers, which are pretty good, that we use in laser pointers and so forth. So we developed the technologies first, and then we knew the scale, the size of the problem, and what had to be done. And it required a big instrument. So the instrument is actually 2.5 miles on a side. It involved fancy electronics and computing and special lasers and very good optics and so forth. And all this took small specialized teams. And when you add the teams together, it adds up to a large number. Actually, the number of people working technically on the instrument is hundreds. The rest are people that look at the data and analyze it, that do the physics.
If I'm recalling correctly, it was the termination of federal funding to a lab in Texas that facilitated this process.
I was involved in this because Caltech was involved, and I helped initiate it at Caltech. And we had the small group doing the technical work that I was talking about, but I wasn't involved hands-on. Instead, my background had been in elementary particle physics using very large particle accelerators. And I was the co-leader of one of two teams that were going to exploit the super collider that was to be built in Texas. And we had a goal to build a detector that could detect what's called the Higgs boson, which was finally discovered instead of us doing it because our machine was turned off at CERN. So rather than discovering the Higgs boson, I moved to gravity. It was kind of a natural move once the accelerator in Texas was terminated by Congress.
So let's shift from the process to the inspiration. And you've talked about one person who probably had more influence on you than any other scientist, Enrico Fermi.
Yeah. Well, first, Fermi was extremely broad.
Yeah.
And I think one of the challenges is how to be broad enough to do whatever the most important science is and still have the depth to do specialized things. So the problem tends to be that people, as they move into something that's specialized, lose the breadth, and then you basically have a lot of specialists. Enrico Fermi was someone who could calculate and do theory. He did experiment. He was a real leader of a group in Italy. I watched and enjoyed the movie Oppenheimer, like you probably did. Oppenheimer was given more credit, maybe as you do when you make a movie, for some work that I think they would have never succeeded in making the atomic bomb without the work that Fermi did on what was called the pile at University of Chicago. And that's a little snippet in the movie, but turns out to be, I think, the difference between whether they would have kept pursuing this or not. That proved the so-called chain reaction. Yeah. Without the chain reaction, you can't do it. And Fermi was very special in those ways.
And part of it was the breadth, right?
Part of it was the breadth, and a big part of it was the breadth and lack of fear and ability to make mistakes and correct them and to lead, and all the things that kind of make things move forward.
So Fermi is an influence on you. Your pathway to physics was not the sort of smooth, direct pathway that some people might imagine. You didn't go to college to study physics
No.
originally?
No, I didn't. Neither of my parents went to college, and I didn't have any relative that was particularly educated and pointed me. I was very good at math and won some math contests, but I didn't know what you could do with that. I had one special friend in high school that was going to go into engineering, and so I went into engineering. Well, I lived in California and could only go to public university, and I had to choose between UCLA and Berkeley. I lived in Los Angeles, so Berkeley was further from home, so I went to Berkeley. I started as an engineering student and took 2 terrible engineering courses and had a wonderful physics course as a first year of school. And I switched. And the professor I had in physics, I ended up being my advisor when I switched in physics. And he ended up winning the Nobel Prize himself for the discovery of what's called the antiproton, the antiparticle of the proton that makes us all up. And so he had a big, direct, but somewhat distant influence on me. Distant because he was so busy discovering the antiproton that he didn't have much time for me, but he had a big impact on me as an undergraduate, and he got me to go into doing some research when I was even an undergraduate. So even though I was a late starter going into physics, not until a freshman, by the time I was a junior, I was doing research already, which most students in those days didn't. And I learned all about particle accelerators at that time, and that's what I pursued for a while.
And your curiosity about the physical world, you talked about how that was evident in some of the questions you were asking and some that your father wasn't able to answer.
I think in general, you picked the right word. I think the key word for doing science and what drives people to do fundamental science, not to build a new, better instrument or something, is curiosity. And curiosity is something that always interests me because we have an expression called curiosity killed the cat, for example. And I think it means, the way it's used, it kills the kind of scientific curiosity that most potentially good scientists have at a young age. I mean, I think when we worry about science education and so forth, we have to ask how sociologically we approach children, because the thing that makes science so attractive is answering your curiosity. If we have an attitude that curiosity is a bad thing, and kids who ask too many questions, we tell them to stop. I somehow escaped that, and I think many of my colleagues, that's kind of, we had an escape route to get to where we are. But curiosity is a key word, I think.
So your part of your curiosity was as a very young person was why does ice float on water?
Yeah. So one of the first times I asked my father a question he couldn't answer was why ice, which is made out of water, floats on water. I mean, what's happening? He couldn't answer me. Of course, the answer is when water freezes, it slightly expands. So it's lighter for the same size as water. And so
But the next logical question was,
why does it expand? Yeah, so there's a whole series of questions. So the first answer is one. And that's kind of the story of science. You basically answer, you unpeel an onion. You find more and more as you go deeper. But that was the first, basically it illustrates that I was curious as a kid, but maybe the first time that I can remember where curiosity and somebody not being able to answer what I wanted to know drove me toward science. It drove me, I think, earlier to being a great fan of libraries, and I learned I could look things up and learn about things in libraries at a young age.
So now one of your really important roles, and people might be surprised by this, but one of your really important roles at Stony Brook is working to cultivate the curiosity of undergraduate students. You haven't, since you came here to join us, been focused just on graduate students, but a lot of time with our undergraduates. What's your biggest takeaway from this?
I just came from my first class with undergraduates, and I had a technical problem. The slide projector when I walked in didn't work, which is maybe you'd say it's a nightmare, but in some sense a blessing. It meant that I had an hour and a half of interacting with them without the burden of a bunch of slides. And I think my interaction with undergraduates is actually to, if you want, stimulate their curiosity. We teach them a lot of book learning. What's going to drive them if they don't know what to do with it at the end? And there's a big gap between learning quantum mechanics and doing physics. Quantum mechanics is very hard. So somehow making them aware of what is new in physics, what's exciting, why we ask certain questions, which ones we can't answer, how we make mistakes. All those things bring life to doing science, and I share it with the kids.
Yeah.
So it's
they're very fortunate to have you sharing it with them. I want to shift from the Stony Brook landscape to the national landscape, and you've talked about the importance of the NSF, how it is absolutely foundational to foundational research.
Yes.
There have been moments when federal support for the sciences have waned a little bit, but it's been pretty consistent, really. For not, people talk about the post-World War II era and federal investment in science, but federal investment in science can really be traced back to the early 20th century in the United States. So whether it's 75 years of it or 100 years of it, do you feel confident that we have enough of a tradition of investment in fundamental science that it will be sustained?
I don't know, to be honest with you. I think science is tough. It's really hard. And if you don't appreciate it and support it in the right ways, you don't make the kind of progress, because there's a lot of failure involved. And there's a lot of wrong ideas, and there's right ideas, and so forth. And I think if you have the attitude that everything has to be measured in traditional ways, that small steps you can't do well, you have to tolerate failure. The National Science Foundation is extremely good at that, but not good enough, really. They have a system that they recognize of approving who gets funded for science based on what we call peer review. So you have an idea, you need money, you propose to the National Science Foundation, they send it to well-known scientists secretly, and they judge what you have proposed. But that system itself, we rely on it, I believe in it, but it's conservative, because something that's radical that you propose isn't going to have referees say yes. So how to support science in a fundamental way and make it move forward, you have to be able to tolerate new radical ideas, failures, all the things that are really tough. This NSF really tries to do that. They tried to stimulate experiments that aren't doing research that isn't supported well by the peer review system, for example. They haven't figured out how to do it well, but no other institution that I know of even comes close to that kind of approach. That the mission statement of the National Science Foundation is one word: it's science. It's not a long paragraph saying things, but it's science. And they've had, as the director of the National Science Foundation, a whole series of rather prominent scientists, not administrators. And I think the National Science Foundation has a really wonderful record up till now and a good approach. And yet it's not the best you could imagine that we somehow do things that are more, as I say, tolerate failure more.
Right. In a world where ROI, return on investment, seems to shape so much thinking, the NSF may be doing better than just about any other organization.
They do. But as I said, the peer review system by itself, they use people like me to referee. But of course, if somebody has a radical idea that I don't really appreciate, I'm not going to give it the best possible review. So it's a really tough problem, how to do the best, and they do really well.
What would you say to young people considering physics as a major today? Encourage them to go into the field?
The last century has been amazing, and I think the next century will be even more, in that we are developing tools and abilities to understand the basic laws of nature. And maybe even the basic laws of nature are different here than somewhere where the early universe was or something. But the laws that we know here, we're able to test. And I think the opportunities are great because we have the tools and wherewithal to do it. And science and the amount that society benefits from science is enormous and hard to quantify. Just because of scientific inventions like penicillin, which was an accidental invention, lengthened our lives on the average by a decade. That was the 1920s. The discoveries, I mentioned two, in fundamental physics that you'd think have no effect on anything, but they do. One was in the 1960s, the discovery of what's called stimulated emission. Stimulated emission was proposed by Einstein in 1919. They were testing an idea by Einstein. It turned out to be right, and it focuses light in a particular way. It was more than a decade later that we learned that it could be used to make what we now call lasers, and that's a $100 billion industry now, lasers, which wouldn't be here without the fundamental research that was done. That was when I was a student. It was done in Berkeley, the original research. And then I was working in Cornell in the 1970s or 80s, and there was research on another very fundamental idea called totally physics, nuclear magnetic resonance. It turned out that that was discovered several places, partially at Cornell. And again, nobody knew immediately that it had use, but it's now our best imaging device in medicine. They dropped the word nuclear because people don't like the word nuclear applied to things, but it's magnetic resonance imaging, or MRI, came about just because of an absolutely fundamental physics experiment, not because of trying to develop a widget somehow.
Right. Barry, I'm thinking about a project that I'm working on the American writer John Steinbeck, who received the Nobel Prize in 1962. It was it's a huge part of the Steinbeck story, but that's for another time. But I just wonder, how do you learn about the Nobel Prize? It's not over email, right? Somebody gives you a call, or
no. The Nobel Prize is awarded on the anniversary of Nobel's birthday, which is December 10th. So every year it's given December 10th at noon, Stockholm time.
Right.
And it's a big secret until it's announced at that moment. And they announce them in series, the physics, chemistry, literature, and so forth.
So you got a call?
Yeah, so I was in California, where I live otherwise. And when it's noon in Stockholm, it was, I think, 2 in the morning or 3 in the morning in California. So
you think they would have some practice in figuring out the time difference?
Well, no, they want to put on a show in Stockholm. Right. So it's a big television thing in Stockholm and on the internet and so forth. It just turns out California is partway around the world. Yeah. So in my case, we had, you don't know, there's no such thing as rumors. There's no inside word that I know of. But we had some realization that we would be strong candidates to get it that year even. But you didn't know. There were various preparations in case it happened the day before at my other institution at Caltech. So they prepared for a possible press conference and actually drafted a press release a day before. So that was uncomfortable for me at Caltech because you don't know you're going to not get this thing, and they're acting like they're preparing for the eventuality. But they have to react very quickly because it comes out. So anyway, I was with my wife, and we went to bed. I made a concession of moving a telephone. We don't keep a telephone in the bedroom. We moved a telephone into the bedroom. They're portable these days, so you just moved it in the bedroom. I set the alarm for whichever it was, 1:45 or 2:45. The alarm went off. I woke up. I actually did fall asleep despite the anticipation. And the alarm went off, and I just assumed, well, somebody else got it. I didn't get it. Yeah. But I got up and went to go into my study to watch on the internet. Right. And as I was walking, my cell phone started ringing. Not my home phone, but my cell phone. To this day, I have no idea how or why they got my cell phone number. I don't give it out that much. But they called on the cell phone. It was a very distinguished Swedish voice, so there was no feeling that it might be a hoax. It just came across very strongly. And it was brief. He said, "I've got good news. You and your colleagues have been awarded the Nobel Prize." And he said a few other words about, you come December 10th and blah, blah, blah. And then he asked me how do you feel about it? It was a funny question to ask after you've talked to somebody for 3 sentences. But he asked me, and I said, well, I can't think of a single word, but I'm both humbled and thrilled at the same moment.
Yeah.
So that was that. And then there was all the excitement of about 20 minutes later, it was announced, and our phone started ringing immediately, and a lot of excitement and press conferences and this and that. And then eventually you go off to Sweden, and they have 1 week of activities you go through, which involves everything you can imagine, from partying to going to the parliament and talking to the members of the parliament to lecturing to high school kids. And they fill up a whole week of festivities.
Yeah, I know that Steinbeck agonized over his trip to Sweden and the speech that he wrote. He wrote multiple versions before he got to what he wanted, and I've seen the words that you shared there at the ceremony. Yeah,
maybe the speech had less latitude for me than for somebody in literature, but and I won it along with 2 colleagues, so we had to coordinate who covered what, because we gave 3 talks, not 1 talk like he had to give. And that took some preparation. The whole thing is kind of unreal and, obviously very exciting.
How did it change things for you after the prize is awarded, after you've come back and you have interactions with colleagues, you have interactions with students, you're the same person. It was you that won the Nobel Prize.
I know what you're asking, and it's still uncomfortable. I mean, I'm a celebrity, but I was never a celebrity. And no matter where I go, especially in scientific areas, students and so forth, so they all want to take selfies with me, and, all that kind of stuff. And I've grown used to it, but I didn't live that way until I won the Nobel Prize. So it's a bit of a change in life. The other big change is that you're automatically, if you're a Nobel Prize winner, taken seriously, whatever you say. As a scientist, there's a lot of things that we may not agree with that are being done in the world or in our government or anywhere, and all of a sudden you're listened to when you talk about something, for example, global warming or something where it may have some relevance to science. It's hard to get anyone to listen to scientists talk about global warming, but having the addition of a Nobel Prize gives more cachet. And so I feel a certain responsibility, beyond the celebrity part, I feel a certain responsibility as a kind of representative of science in various ways that I didn't have before.
And Barry, here at Stony Brook University, our students, our undergraduate students as well as our graduate students, get to take courses with you, a Nobel Prize winner. So how lucky they are, how lucky we are to have you here. And thanks for being here and being an incredible resource for our students as they developed that level of curiosity that drove you to such important breakthroughs in science?
It's a treat for me. It's a wonderful place, and it's a great set of young, eager students who are being supported by the state, and I believe in public education, and you're doing a great job here.
Wow. It's wonderful to have a university that's as committed to social mobility as Stony Brook is, and the physics department is undergoing a real, should we say, renaissance. It's always been a great physics department, but major growth in the undergraduate major in the last several years.
Yeah. And I just came from my undergraduate class, and it's great. So it keeps me young.
Barry Barish, thanks so much for joining us on the 100th anniversary of Einstein's predictions concerning gravitational waves. Thanks for helping us to understand.
Well, thank you for having me.
Yeah.
And,